Hello everyone, welcome back to Max 20. Today we are evaluating integral over c z sec z divided by 1 minus z all square dz over the region mod z equal to 3 using residue theorem. So this is our question. Z sec z divided by 1 minus z all square is our function and we want to integrate over the region mod z is equal to 3. And we know that sec z is 1 by cos z. You know the singularity z equal to 1 is a singularity. Z equal to 1 is clearly a singularity and it is a pole of order 2. Order is 2 since sec 1 is not 0 and z equal to 1. Numerator is not equal to 0 for z equal to 1 and denominator is a 0 of order 2. Therefore, z equal to 1 is a pole of order 2 of this function. Also, there are many singularities because this function is sec z. Sec z is not an analytic function. That means sec z is 1 by cos z. We know that cos z is analytic but 1 by cos z has singularity because cos z equal to 0 when z is equal to 2n plus 1 pi by 2. That means the values are for n belongs to z integers. That means the values are pi by 2, 3 pi by 2, 5 pi by 2, etc. And also the negative integers, that is minus pi by 2, minus 3 pi by 2. These all are zeros of cos z. Therefore, these are singularities of sec z and these are poles, symbol poles. These values are symbol poles of sec z. Since sec z is in the numerator, we have these singularities and we now want to check mod z equal to 3. That means which of these singularities are inside the region mod z equal to 3. We know that 3 pi by 2, 5 pi by 2 etc. are greater than 3. Also minus 3 pi by 2 are not inside the region mod z equal to 3. This is 3 radius circle with the center 0. So pi by 2 and minus pi by 2 is inside the region. Therefore, these are singularities of sec z in mod z equal to 3. Also, we have the singularity z equal to 1. These are symbol poles and z equal to 1 is pole of order 2. Therefore, we have 3 singularities here. Now, we use residue theorem to evaluate this integral. That is integral over c z into sec z divided by 1 minus z all square dz, which is equal to, by residue theorem, this is equal to 2 pi I into residue of singularities inside the region mod z equal to 3. We know that there are 3 singularities inside the region of this function. That means residue at z equal to 1 f of z and next residue at z equal to pi by 2 f of z and next is residue at z is equal to minus pi by 2 f of z. So this is by residue theorem 2 pi I into residue of residue at singularities inside the region. Now let's calculate the residue of f of z at z is equal to 1. We know that z is equal to 1 is pole of order 2. Now we have the formula residue of function, a function at the pole of order n is 1 by, this is 2, 1 by 2 minus 1, 1 factorial. If you are not familiar with this formula, please watch my previous videos of residues. This is 1 by 1 factorial, limit z tends to 1, d by dz of z minus 1 all square into f of z. And limit 1 factorial is 1, z tends to 1, d by dz of z minus 1 all square and 1 minus z all square are same, into f of z is z sec z. Now let's take the derivative and take limit. And this is of the form u into v. So first function into derivative of sec z is sec z tan z plus second function sec z derivative of z is 1. Now putting limit, we get sec 1 tan 1 plus sec 1. This is residue at z equal to 1 of f of z. Now we calculate residue at z is equal to pi by 2 of f of z. We know that pi by 2 and minus pi by 2 are symbol poles. Now residue at a symbol pole, we have the formula limit z tends to pi by 2 z minus pi by 2 into f of z. These formulas, all formulas and some examples are I described already in my previous videos. And this is equal to limit z tends to pi by 2 z minus pi by 2 into f of z is z sec z divided by 1 minus z all square. And we know that z, when taking limit, this is sec pi by 2 and this is z, this is 0. For the convenience, we can use z tends to pi by 2 z minus pi by 2 into z. This is 1 by cos z. Sec z is 1 by cos z. That means cos z into 1 minus z all square. Now taking limit z equal to pi by 2. This is 0. Numerator is 0. Also denominator is 0 since cos pi by 2 is 0. Therefore this is 0 by 0 mode. We can use a L'Hospital rule, that means differentiate numerator and denominator with respect to z. Derivative of numerator. This is u into v form. Z minus pi by 2 into derivative of z is 1 plus z into derivative of z minus pi by 2 is also 1. So just divided by, now this derivative cos z into derivative of 1 minus z all square is 2 into 1 minus z into minus 1 plus 1 minus z all square into cos z derivative is minus sin z. Therefore, now taking limit z equal to pi by 2, this is 0 and z equal to pi by 2, there is pi by 2. Now cos pi by 2 is 0, thus this term becomes 0. And this is minus of 1 minus pi by 2 all square, sin pi by 2 is 1. And this is equal to pi by 2 minus pi by 2 divided by 1 minus pi by 2 all square is 2 minus pi all square divided by 4. That will go to the numerator, and this is minus 2 pi divided by 2 minus pi all square. Now let's calculate residue at z is equal to minus pi by 2. Residue at z is equal to minus pi by 2 f of z equal to limit z tends to minus pi by 2 z minus pi by 2. That means z plus pi by 2 into f of z is z sec z. Sec z is cos 1 by cos z. So put it as denominator into 1 minus z all square. Again, we putting limit z equal to minus pi by 2, we get 0 by 0 form. So, taking derivative of numerator and denominator, this is z plus pi by 2 plus z divided by cos z into 2 into 1 minus z into minus 1 plus 1 minus z all square into minus sin z. Now taking limit z equal to minus pi by 2. This is minus pi by 2 divided by cos minus pi by 2 is 0. So this term becomes 0. Now 1 minus z minus pi by 2, that means 1 plus pi by 2 all square minus sin pi by 2 minus of sine of minus pi by 2. Sine of, you know that sine of minus x is minus sin x. So sine of minus pi by 2 is minus sin pi by 2. Sin pi by 2 is 1 or minus is plus. So we get minus pi by 2 divided by 2 plus pi all square, all divided by 4, go to the numerator. This is minus 2 pi divided by 2 plus pi all square. This is residue at z equal to minus pi by 2. Now the value of integral is integral over c z sec z divided by 1 minus z all square dz equal to 2 pi I into residue, sum of these residues. First we get residue at z equal to 1 is sec 1 tan 1 plus sec 1 and z equal to pi by 2 is minus 2 pi divided by 2 minus pi all square, and this is minus 2 pi divided by 2 plus pi all square. So the final answer is 2 pi I sec 1 into tan 1 plus sec 1 into tan 1 plus 1 and minus 2 pi is common there. This is 1 by 2 minus pi all square plus 1 by 2 plus pi all square. If you want to simplify this, you can simplify, or this is our final answer. If this is helpful to you, please like this video and subscribe my channel. Thank you for watching.